When you're building with machine learning models, debugging can feel less like engineering and a lot more like a super frustrating mystery. But what if you had the skills of a detective? Today, we're going to turn that frustration into a systematic investigation. So let's get right to it and look at our prime suspect. Oh, yeah. This one. If you've worked with GPUs, you've probably seen this cryptic message. It's the kind of error that just stops you dead in your tracks, gives you absolutely zero clues, and makes you question every life choice you've made up to this point. Look, if this has happened to you, you're definitely not alone. This is one of the most common and honestly confusing parts of the whole process. But the good news is, there's a method to this madness. There's a way to see right through these confusing messages to find the real culprit. All right, so it's time to put on your detective hat. We're going to approach this problem not with frustration, but with a clear, step-by-step investigative technique. Our goal? To crack this case wide open. So here's the game plan for our investigation. First, we'll examine the problem. Then we'll lay out our method. From there, we'll trace the data trail, unmask that infamous CUDA error, figure out how to solve silent failures, and finally, we'll put together your complete debugging toolkit. Every good investigation starts at the scene of the crime. And for us, that's the moment you hit trainer.train, and everything just grinds to a halt. You've been called in to figure out what went wrong. And this is what makes it so tough, right? The trainer is kind of like a black box that's handling a ton of complex steps all at once. The error could be hiding anywhere in that chain. It's like having a crime with way too many suspects and not nearly enough clues. So how does a detective handle a complex case? Not by guessing, that's for sure. They follow a clear, systematic procedure. So we're not just going to stare at the error message, we're going to get our hands dirty and manually retrace the codes every single step. And this is really our guiding principle here. The idea is to break open that black box and look at each component one by one. This is exactly how we're going to find the one piece of the puzzle that just doesn't fit. Okay, so here's our four-step plan of attack. We'll start with the raw evidence, the data itself. Then we'll check how it's being prepared for the model, see what the model is actually doing with it, and finally check the learning step. Let's get started. All right, every good investigation starts with the evidence. And believe me, 9 times out of 10, the mystery begins and ends with the data. What was the machine actually looking at? And right away, we find our first clue, and it's a classic. The error log is talking about input IDs, numbers. But when we inspect our dataset, we see raw sentences. The model is getting words when it expects numbers. Basically, someone forgot to tokenize the data. And would you look at that? It was a simple typo. Someone passed in the raw datasets instead of the tokenized datasets. It's a super common slip-up, but our manual check caught it right away. Case closed? Well, not so fast. So we fix one thing and wham, another problem pops up. This time, the error happens when the trainer tries to group our individual examples into a batch. This points our magnifying glass directly at the next suspect, the data loader, and specifically, the data collator. Okay, so what's going on here is this. Without the tokenizer, the trainer uses a default data collator that has no idea how to pad sentences to make them the same length. It's missing a key piece of information. And the fix? It's actually super simple. Just pass the tokenizer into the trainer's arguments. That gives it everything it needs to build batches correctly. All right, so we fixed our data, we fixed our batching, we run the code again, and bam, we get that infamous, terrifying CUDA error. But this isn't just a clue. This is a classic red herring, and it's designed to throw us completely off the trail. So let's break this down. A CUDA error is kind of like a smoke alarm going off in the hallway. It tells you there's a fire somewhere in the building, but it doesn't tell you which room it started in. It only gets triggered at a synchronization point, which is usually long after the real problem happened. Okay, this right here is probably the most important trick in the book for these kinds of errors. Seriously, forget the GPU for a second. Move your code to run on the CPU and try it again. Suddenly, that vague CUDA error vanishes, and in its place, we get this beautiful, clear index error. Now that is a real lead. It tells us exactly what went wrong. And there it is, the real culprit that the CUDA error was hiding all along. The CPU's error message told us it saw a label 2, but our model was only configured for 2 labels, 0 and 1. It's just a simple configuration mismatch. All we need to do is tell our model to expect 3 labels instead of 2. Just when we think the case is closed, one last little puzzle appears. this time during the evaluation step. Turns out, the model outputs raw scores, or logits, but our metric is expecting a final definite prediction. All we have to do is pop an argmax into our computemetrics function to turn those scores into the final prediction. Okay, but now let's talk about a totally different kind of mystery. What happens when there are no errors at all? The code runs, the training finishes, but your model's performance is just terrible. This is the cold case, where there's no obvious crime, just a really unsatisfying outcome. And honestly, this can be even more frustrating than a crash. You start wondering, is my data bad? Is the model architecture wrong? Is my learning rate totally off? We need a way to test if our model is even capable of learning anything at all. The answer is a powerful sanity check called the one-batch overfit test. You basically force the model to memorize just one single batch of data. I mean, if it can't even do that, if it can't get perfect accuracy on data it sees over and over again, then you know you've got a much deeper, more fundamental problem. But if it passes, you know your model can learn and the issue is somewhere else. All right, we've cracked the case, from those cryptic crashes to the silent failures. Now let's pull everything we've learned together into a kind of detective's handbook that you can use for your own investigations. Here are the 5 golden rules for any debugging detective. First up, always go manual and break down the pipeline. To unmask those CUDA errors, always debug on the CPU. Remember to always check your data first. That's where the bug usually starts. For those silent failures, use the one-batch overfit test. And finally, save yourself a ton of time by making sure your evaluation loop works on its own before you kick off a long training run. So, the next time you're staring down one of those cryptic error messages, don't get frustrated. See it as the start of a new case. You have the tools, you have the method. The only question is, what mystery are you going to solve next?